Hello everyone. So in the last session, we have seen your DAC, digital to analog converter. Now in this session, we are going to see your analog to digital converters. Okay. So analog to digital converters. Okay. So this is the most important. This is from the topic from where maximum questions are asked. Okay. Analog to digital converter. So what is this analog to digital converter? In analog to digital converter, basically our input is one analog signal. Okay? Input is one analog signal. Corresponding to this analog signal or analog voltage, we get one digital output. Okay? So this is your ADC. So this is your digital output. Now there are various types of analog to digital converter. One by one, we will see all of them. Okay. So the first one we have is what? It is your parallel comparator type ADC. Okay, parallel comparator type ADC we have. So let us try to draw one 3-bit parallel comparator type ADC. So for that, we have over here is series of resistor. So let me draw it over here. Okay, so we have over here are 8 resistor. Now these resistors have different, not different values, you can say. The first resistor is R by 2 and the last resistor is R by 2. All the else resistor are R and R. So as this is 3-bit, we will have 8 resistor. If it was 2-bit, we would have had 4 resistors. Okay. So here we have what? We have 3 bits. So that is why we have over here is 8 resistors. Okay. So now over here we have, so let me take this over here. So we have VA. VA is the applied analog voltage. Okay. Now let us see. So you can see there will be op amps over here. We have op amps also. So 1, 2, 3, 4, 5, 6, 7. Fine. So we will have 7 op-amps also over here. In what kind of mode is this? Can anyone tell? So this is working in your comparator mode. We will see now. Okay. We have over here one D flip-flop. Now why we use this D flip-flop, that also I am going to tell. And then we have over here one priority encoder. Okay. This is clock of the circuit, because as there is a flip-flop, so we require what? We require one B2, B1, B0. Okay, and this is your priority encoder. Okay, priority encoder. So over here, what is the working principle of this parallel comparator type ADC? Okay, so look, I am writing output of this one as C1, C2, C3, C4, C5, C6, C7. So now look, basically this, what we know, that this all are ideal comparator, means ideal op-amp, and in an ideal op-amp no current goes inside the op-amp. So that means all these resistors are in series. So if it is in series, we can apply voltage divider rule. Okay, we can apply what? We can apply voltage divider rule. So let us try to do that. So voltage at this point, it will be VCC by R into 14. VCC into R by 14. You can calculate it. This point will be VCC 3R by 14. This point will be VCC 5R by 14. This will be VCC 7R by 14. Okay. This will be VCC 9R by 14. This is VCC 11R by 14. And this point is VCC 13R by 14. Okay. So now look, basically this D flip-flop is used to synchronize the output of all the comparators. Okay, it is used to synchronize the output of all the comparators. And this VA is basically the analog input voltage. Okay, or you can say basically this is what? This is your applied voltage. Now make one table over here. Okay, table. For different values of VA, we will have different output. How? So look, first let me write VA over here. So over here, let me write C1, C2, C3, C4, C5, C6, C7. And here it is B2, B1, B0. So look, when value of VA, it is less than VCC into R by 14. So that means, sorry, so what is the least value? Yeah, VCC by R into 14. So what will happen over here when the value is less than even VCC into R by 14. So all the comparators, it will produce zero output. Why? Because this, if you have even your applied voltage is lesser than what? If it is lesser than the applied voltage, means look over here, this voltage is VCC R by 14, but if I apply a voltage that is even less than this, so non-inverting terminal is at higher potential, whereas inverting terminal is at higher potential compared to non-inverting terminal. So all the comparators will produce zero output. So this is 0, 0, 0, 0, 0, 0, 0. So for that, basically what will happen when we get all the input 0, 0, 0 of priority encoder, over here we will get 0, 0, 0. Now if suppose my applied voltage is in between VCC 3R by 14, VCC R by 14 and VCC 3R by 14. Okay. So what will happen? You can see this comparator C1, it has value, its inverting terminal has a value greater than the non-inverting terminal. But remaining all the comparators have its non-inverting terminal at a lower potential than its inverting. So that is why C1 will be 1 and all of them is 0. So when C1 is 1, so this will correspond to 0, 0, 1. Similarly, for the next case, it will be what? When your applied voltage is between 3R by 14 and VCC 5R by 14. So at that time, basically you can see this C2 and C1 both will be 1, whereas all the remaining comparators will be 0. But as C2, if C2 is 1, so that means whatever is the value of C1, it doesn't matter because this has been supplied to the priority encoder. So I should have written, because this is the C1, C2. So this is 1. So as these are given to the priority encoder, so this will correspond to 0, 1, 0. Similarly, like this, we can have all other your output combination for a particular value of VA. Okay. So this is what? This is your parallel comparator type ADC. Now, over here, what I told you that this D flip-flop, it is used for synchronization. What if your comparator has different delays? Okay, comparator has different delays. Then D flip-flop, what it will do? It will particularly give all the output of the comparator, respective comparator, at a particular active edge. So here I have assumed it to be a positive edge trigger. So it will give all the output at a positive edge. Now for a 3-bit ADC, what are the number of comparators required? Number of comparators over here is 7. What if it is your n bit? For n bit, it will be 2 to the power n minus 1. Okay, 2 to the power n minus 1. Number of resistors? Number of resistor in this case is equal to 8. For n bit, it will be equal to 2 to the power n. Okay, 2 to the power n. Now this is also known as your simultaneous comparator ADC or flash type ADC. So I'm going to write it over somewhere over here, or else it's okay. Let us write over here. What it is called as? Simultaneous comparator ADC or flash type ADC. Okay, flash type ADC. And this is the fastest ADC. Why? This is the fastest ADC because over here the conversion time is what? It is just one clock pulse, one clock cycle. So this is the fastest ADC. Why? Because you can see all the comparators, it will give output in just one clock. And this priority encoder, it is basically a combinational circuit. So the moment it gets its input, immediately you will get your output. So okay, so here this is the fastest type, but it is costly also due to the fact that there are multiple comparators required over here, and it is what, it is bulky also. So usually we don't use this kind of ADC. We use it wherever we require very fast output. Okay, wherever we require very fast output. Now next we have is successive approximation type. Successive approximation type. Now before understanding this successive approximation type, okay, so let us understand one example. Okay, let us understand one example. So you might have seen this weighing scale in your vegetable market. Okay, so here we have this pointer, and here we have the scale. So whenever we want to balance it, so at one point we have your basically the standard weights, and here we keep the vegetable to get the equivalent weight. Okay, to get the equivalent weight. So let me write it as vegetable for V. If suppose we have three weights, okay, we have three weight bar. So it can be of half kg, it is of 1/4 kg, or it is of 1/8 kg. So now how do we basically get to the conclusion of weighing, means getting this vegetable? So look over here. First case, I am starting from half. Okay, I am starting from half kg. If suppose you keep the vegetable and you load over here with half kg. So now there are two possibilities. Okay, there are two possibilities. What? Either what will happen, either it will be more or it will be less. Okay, either the weight will be more or it will be less. So what is happening, either the weight will be greater than half or weight is less than half. So when weight is greater than half, what will I do? I will load this 1/4 also. And if weight is less than half, what will I do? I will remove this half kg and load it with 1/4 in this side. Now once again for this case, there might be two cases. So this is what, this is basically your, if this value, okay, if now weight is greater than 3/4 or if weight is less than 3/4. So if it is greater than 3/4, so what we'll do, half plus 1/4 plus 1/8, we are going to load it. Okay, we are going to load it. Or this will be lesser than, so what we are going to do over here, I will remove this 1/4 and replace it with 1/8. Okay, or over here what might happen, this weight might be greater than 1/4 or it will be less than 1/4. If it is greater than 1/4, then we are going to load 1/8 also. And if it is less than 1/4, so we will remove this 1/4 and we will load it with 1/8 over here. Okay, we will load it with 1/8. So now what all things we got? Now one more we will get, either your weight is greater than, so this is what, this is your so 7/8, or if weight is less than 7/8. over here this is weight is greater than 5 by 8 or weight is less than 5 by 8. Over here this is what weight is greater than 3 by 8, or if weight is less than 3 by 8 or weight is greater than 1 by 8 or weight is less than 1 by 8. So this basically you can see I have loaded all the weights. So this will correspond to 1, 1, 1. Here you can see basically if weight is less than 7 by 8, so I will remove this 1 by 8. So this will become 1, 1, 0. Okay. If weight is greater than 5 by 8, okay, if weight is greater than 5 by 8, but it is less than 7 by 8, so I will be doing what? Half and 1 by 8. So this will be 101. And in this case, basically, I will remove this 1 by 8 also. So this will be 100. This over here, it will be 011. Over here, this will be 010. This case is what? It is 001. And last case is 000. Okay, because if weight is less than 1 by 8, we don't have the proper weight over here, standard weight to measure it. Okay, so this is basically the main property that we are used for our successive approximation type ADC. Okay, successive approximation type ADC. So the number of comparisons that we took over here, it is 3. Okay, number of comparisons that took, it is 3. For n bit, it will be n. Okay, so now basically see how this thing actually works, successive approximation type. Okay, so look, so this is up counter, this is your program. Okay, over here we have clock. This is given to a latch. Okay, so this is basically the input that we are going to take. See what is happening over here. So instead of writing this as program, let me write it as up counter. Okay, up counter. So if suppose this is one DAC that has your step size of 1 volt and it is 3 bit, that means for 000 it is 0 volt, for 001 it is 1 volt. Similarly for your 1111 it will be what? It will be 7 volt. Okay, it will be 7 volt. So now look, what is means how over here it everything is happening. So if suppose VA I give it to be as 6.2 volt. Okay, I gives VA as 6.2 volt. So look over here, basically we have clock pulse over here. What is the value of up count? Counter. Okay, up counter. Then we have over here DAC output. Okay, and over here we have the output of comparator. Output of comparator. So now look, So here applied voltage is 6.2. So when clock pulse is 0, initially all the counters are resetted. So this is 0, 0, 0. Okay, this is a 3-bit up counter. So DAC output is what? It is your 0 volt. So you can see this is your non-inverting terminal. This is your inverting terminal. So what will happen? Output of the DAC is 0 volt. So this is 0, this is 6.2. So what will happen? A high will be generated, high signal will be generated, and this up counter will count to 1 in your next clock pulse. I am writing V plus is greater than V minus, means inverting, non-inverting is greater than inverting. So in the next clock pulse, basically it will count up. Now once again you can see DAC output will be 1 volt. Once again V plus will be greater than V minus. Similarly, in the second clock pulse, once again you can see this will be 0, 1, 0. DAC output will be 2 volt, V plus greater than V minus. Third clock pulse, this will be 0, 1, 1. This will be 3 volt. V plus is still greater than V minus. Okay. Now in the fourth clock pulse, 1, 0, 0. So this is 4 volt. V plus greater than V minus. In the fifth clock pulse, what will happen? This is 1, 0, 1. This is 5 volt. V plus is still greater than V minus. In the sixth clock pulse, what will happen? This will be 1, 1, 0. So this is 6 volt. So this is V plus is still greater than V minus. Now look in the seventh clock pulse. What happened? This become 1, 1, 1, and this is 7 volt. Now V plus is less than V minus. So what will happen? This, which state do you think will be the declared state of this ADC? Sorry, I should be making one latch. This is the latch, and the output of this latch is basically the output of ADC. So what do you think? ADC will select which output, 110 or 111, when VA is equal to 6.2 volt? So basically over here we have a latch. So latch will select this previous value, because up to this point my condition was true. So that is why output of this ADC will show 110 as its output. Okay. So this will be the declared state of your ADC. So this is how basically we design one successive approximation your ADC. Okay. This is your successive approximation ADC. Now over here, if I ask you what is the maximum conversion time? Maximum conversion time. So maximum conversion time is basically the time taken by the ADC to convert the maximum output. So over here, if I put 7 volt, so it will take 7 clock cycle. It will take 7 clock cycle or 7 TC, because each of this is 1 clock pulse. So for producing 7 volt, it will get, means we will get 111 over here after 7 clock pulse. So if this is your n bit, then it will be NTC. Okay, it will be NTC. So sometimes what happens basically that we have to create one simple circuit. So this is one very simple circuit, but over here you can see we are just using one single comparator, this one, instead of using 7 different comparators. Okay, so this is one advantage of this kind of ADC from the previous ADC. Okay, previous your flash type ADC. So now over here I told you basically the maximum conversion time is 7 TC, okay, or NTC. Now how do we actually reduce this conversion time? So for that, if suppose we have a same circuit, now I am taking. Now this time, instead of using up counter, we have a program over here. Okay, program. program. So now how do basically we reduce the conversion time over here? So see, if we have 6.2 volt, so what happens? See over here, if this is your bit B3, sorry, B2, B1 and B0. So initially this DAC means, or the program I should be writing, so over here we have this comparator. So look, when we start at clock pulse 0, all the counters are 0, 0, 0. At the first clock pulse, this program, what it will do, the MSB bit position will be 1 and remaining all the bits will be 0. Okay, remaining all the bits will be 0. So if that is the case, you can see this is 4. So your comparator will be what? V plus is greater than V minus. So in the next case, what will this program do? It will keep this MSB intact and it will increase, means it will change the next bit position. So now this has become 6. Now 6 is also greater than 6.2. So V plus greater than V minus. In the next case, what will happen? The next bit position will become 1. So here you can see V plus is less than V minus. That means this value will be shown in the latch. Now if suppose instead of 6.2 it was your 3.3, everything else remaining the same. So at the first clock pulse, what will happen? At the 0th clock pulse, all the values are 0. In the first clock pulse, the first MSB bit will become 1. But here you can see if this becomes 1, what is happening? Here you can see that V plus is less than V minus. So in the next clock pulse, this one will convert to 0 and the next bit position will become 1. So now this is 2. So V plus is greater than V minus. So now what will happen? In the next bit, it will be 0, 1, 1. Now you can see basically this is 3, but V plus is greater than V minus. But as this is your 3 bit, I cannot do any more changes over here. So this is basically the output of your DAC. So this corresponds to 3 volt. So there is actually error of 0.3. So here the maximum conversion cycle, previously it was what? It was, you can see, NTC, okay, NTC, where N is basically what? So I am sorry, over here I have written it wrong. So the maximum conversion time was 7 TC. So it is 2 to the power n minus 1 TC. Now in such kind of programmable DAC, so here your conversion time is equal to NTC. So if it is 3 bit, the maximum time that will be taken over here, it is what? It is your NTC. Now the most important ADC, sorry, that we have, it is your dual slope ADC. Okay, dual slope ADC. Now this is the most important ADC and the most versatile ADC that is basically used even in your multimeter and all the industrial purpose. Basically we use this kind of ADC only. So basically what is the internal structure? Let us try to find out. So over here we have two input. One is analog input, another is your reference voltage, and we have one switch over here. See, understanding this circuit is very important because questions have also been asked from this part. So if you see, means over here we have an AND gate also. Okay, so this is one AND gate. We have external clock also. Now this actually acts as your clock pulse for an up counter. So we have one up counter over here. This is MSB, this is LSB of the up counter. Along with that, we have a T flip flop. So the clock pulse is negative edge of this up counter and it is connected to the MSB. This is Q. This is your toggle input, and toggle input is always given as 1. Okay, and this Q is basically connected to this switch. Okay, so we have a switch over here. So now basically what is the construction that we have to see? So let us consider this is a 4-bit ADC. Okay, 4-bit ADC. So now you can see this part. Okay, this part. This is basically an integrator. Okay, this is one integrator. And here we have one comparator, one AND gate. So basically what is happening over here? So suppose this is one 4-bit analog to digital converter. What I am saying, this is your 4-bit. Step by step, let us see. 4-bit analog to digital converter. Fine. So initially everything is 0. Initially the counter is in 0 state. Okay. So now if it is in 0 state, okay, 0 state, so basically what is happening, look over here. So this T flip flop initially means this switch is connected to VA. Okay, this switch is connected to VA. Now tell me, when we have this kind of counting sequence 0 0 0, so this T flip flop is initially connected over here. So it will toggle it. When it toggles basically, so output will change from VA to minus VR. But when will that happen? When we encounter the negative edge of MSB. So when do we encounter the negative edge of MSB? So let us see. So like this, we will have till 0 0 0 till your 0 1 1 1, and the next bit will be 1 0 0. Next will be 1 0 1, and after that we will have 1 1 1 1. So this is your MSB, this is LSB. So try to understand. So from here to here you can see you are going from 0 to 1. So when you go from 0 to 1, you have positive edge. But over here you can see you are changing the MSB from 0 to 1. But the moment you go from 1 1 1 to 0 0 0, that means your MSB is going from 1 to 0. At this time you have negative edge. So when do we encounter the negative edge? So we encounter the negative edge after 16 states, or if this is your n-bit ADC, so you will encounter the negative edge after 2 to the power NTC. So write it over here that initially counter is resetted to 0000. Okay. So the negative edge of MSB we will get after 16 states, or if it is your n bit ADC, so after 2 to the power NTC clock pulse we will get. Okay, so after that we will get. So now basically let's try to understand what is happening over here. Okay, what is happening over here? Let us try to see that. So what is happening? The T flip-flop is a negative edge triggered charging time. Now what is this charging time? See, basically when we have started from 000 till your 1111, what is happening? Look. So this is VA. So this value will be a positive voltage. If this is positive, obviously the output over here will be what? It will be negative, because this is your negative amplifier. Okay, negative feedback amplifier. So what is happening over here? You can see this voltage over here is negative. So this becomes what? This is your negative value, and this is already connected to ground. That means V plus is greater than V minus over here. So you will get digital high output or 1. So this is 1. And for each clock pulse, this up counter is going to keep on counting. Okay, keep on counting. So basically this capacitor is charging in this way up to what time? So this will keep on going till 111. Okay, this will keep on going till 111, because the capacitor is charging continuously. You can see what? That from here we are getting clock and this up counter is going. So here we don't have a negative edge. So this switch is connected over here. But what happens the moment if we change from 111 to 000? What is happening? Now your switch the position of the switch, now it changes from here to here. Okay, it will come over here. So now you can see basically this is minus VR. Capacitor has charged like this. Now you can see this part has positive voltage. Okay, here we have positive voltage, and over here we negative voltage. So the capacitor will start to discharge in this path. Okay, it will discharge to this path up to what time? Till the time this capacitor fully discharges, because when it fully discharges, then V plus is equal to V minus, then once again it will wait for VA. Now what is this VA? VA is the applied voltage. So you can see basically whatever value I take, whether I take 4 volt, 5 volt, 10 volt, charging time, it is the same. Okay, it is the same. Charging time is what? It is up to 16 clock period. Already I have told that basically this is going to change state. This T flip flop is going to change state from where to where? When it changes from 111 to 000. So this capacitor is going to charge more for what? It is going to charge more for 5 volt compared to 4 volt. Now this capacitor is going to charge more even for 10 volt compared to 5 volt. Okay, so basically the capacitor will charge more for your more voltage, hence it will take more discharging time while discharging completely to 0. So basically here we are going to measure the output with respect to the discharging time. So let us try to see that. Okay, let us try to see that basically what is happening. So let us assume, if suppose so this is your T, okay, and this is V naught. So charging time remains the same. Now charging time is how much? Already we have discussed that it is 2 to the power n Tc. Okay, 2 to the power n Tc. I am denoting it with T1. So if suppose Va is equal to 5 volt, so it will charge up to this point. Okay, it will charge up to this point. Now if suppose it is 10 volt, as your input voltage is more, so it will charge more. Okay, if it is even more like 12 volts, so this will even keep on charging. Now look, basically up to this charging point, I hope everything is clear. Now what happens, the moment charging means this switch, it changes state from your Va to minus Vr. What will happen? Basically your discharging will start to happen. Okay, discharging will start to happen, and the capacitor will take more time to discharge when it has more energy, because the value of R and C is same. So tau is equal to RC. Discharging time is 5 tau. Okay, 5 tau. So here you can see discharging time is 5 tau. It is equal to RC. So discharging time remains the same, but for a more amount of energy, it will take more time to discharge. Okay, it will take more time to discharge. So if this was for your 5 volt and this was for your 10 volt, now why have I drawn it in the negative side? Because I told you this is connected in which manner? It is connected in your negative feedback. Okay, so over here this output will be equal to what? This output will be equal to minus 1 by tau. Okay, 1 by tau Va d tau, means sorry, this tau is actually RC. I should write it RC, because this is what? This is your integrator 0 to t. Okay, where t is equal to what you want to write. So this will be T1. Now what is T1? It is equal to 2 to the power n Tc. Okay, so discharging time, it will be like this for this one. Similarly for this one, it will look like this. So it will take more time to discharge. Okay, it will take more time to discharge. So now let us try to basically do what? Let us try to find the relationship over here. Okay, relationship. So let us try to find out for this one only. I am removing this 10 volt. It was just for explaining you that what will happen if we give 10 volt. So let us remove this. It is not required. So let me write this as now minus VA. Okay, so this is minus VA. So if you want to write basically the equation of this, so what will be that? Equation of this line, it will be minus VA by T1. Okay, VA by T1 into T. Okay, VA by T1 into T. What about this line if you want to write? So you can use 2-point formula. So that is what? Y2 minus Y1 divided by x2 minus x1 is equal to y minus y1 divided by x minus x1. So you can use that formula. You can consider this as your x2 y2, and this point as what? This point as x1 y1, and then you can solve it. So now let me assume what? That time over here is t2. Okay, t2. So if we write the expression, so this will be equal to what? Y2 minus Y1. So minus VA minus 0 divided by x2 minus x1. So that is T1 minus T2 is equal to, over here Y1 is what? Y is what? It is V0 minus Y1. So Y1 over here, it is what? It is 0 divided by t minus x1. So that is t2. Okay. So now let us try to write V0. So V0 is equal to VA T2 minus T1 into T minus T2. Look if this is correct or not. Is this correct? Okay. So this is what? This is the V naught we get for this one. This green color line, we got this expression. Okay. So now you can see from here that while charging, if I have to write over here, so what are we getting while charging? So over here, let me write this as VCT. Okay. So VCT is equal to what? VCT is equal to 1 by C integration of idt. Okay. Now what is I over here? So you can see if I apply from here to here KVL, so this will be VA by R. So let us write this 1 by C integration of 0 to T. But I is what? I is your, you can see current flows from higher potential to lower potential side. So that will be equal to minus VA by R into dt, or this is equal to minus VA by RC into T. Okay. Or you can even write this as minus VA by tau into T. Equation 1. Or V naught is equal to what? V naught during this much time. So we have already seen that is equal to VA by tau into T1. Okay, at T1. Now while discharging, what is happening? While discharging, this is while charging. So now discharging, if you see, so V naught is equal to VC initial value, that is till T1. Okay, T1 plus 1 by C integration limit will be from T1 to T I d tau. So this value, if I put the value of T1 over here, so this will be equal to what? This will be equal to minus VA by tau into T1 plus 1 by C. So this will be now T1 to T. So current is what? Current is flowing in the opposite direction. So this will be VR by R d tau. So let us solve this. So this will be equal to V naught is equal to minus VA by tau into T1 plus, so this R will come out. So this is again 1 by tau. This is VR T minus T1. Okay, T minus T1. Now what happens at T2? At T2. So at T2, if I write it over here, at T is equal to T2. So put V naught is equal to, so this will be equal to 0, or 0 is equal to, let me put it over here, minus VA by tau T1, and this is plus 1 by tau VR T2 minus T1 in this equation. Okay. So now if I solve this, so VA by tau into T1 is equal to 1 by tau VR T2 minus T1. So this tau gets cancelled. So it is VA T1 is equal to VR T2 minus T1. Okay. So now you can see basically what is T2 minus T1. So this is T2, this is T1. So this much time is what is your discharging time. Discharging time. So if you see over here, basically what are we getting? So T1, I can write it like VA into 2 to the power n Tc is equal to VR T2 minus T1. Okay, T2 minus T1. So if we have your stable counter, okay, if we have stable counter, so what will happen? The time means this discharging time will be equal to the digital outputs value, this counters value. Okay, whatever is the counters value, same value you will be getting while discharging. So I can write it like NTC. Okay, I can write it NTC. So this TC gets cancelled, or N is equal to VA by VR into 2 to the power N. Okay, so this is what we get. Now over here you can see what basically that this V naught, where is V naught? Over here. If we are somehow able to get, means if you look at this equation, I can rewrite it as VA is your input voltage into T1 is charging time. This is equal to what? This is equal to your reference voltage into discharging time. Okay, discharging time. So you will see a lot of questions that has been asked using this concept. Now one more concept that we need to know over here is the concept of maximum conversion time. Now what is this maximum conversion time? So okay, one thing I forgot to tell, that this n is basically what? N is the number of counts that we get. Okay, number of counts that we get in the up counter, that is directly proportional to what? That is directly proportional to VA. Okay, N is the number of count in the up counter, so that is directly proportional to VA. So now let us talk about maximum conversion time. Maximum conversion time. So that is equal to charging time, which is fixed. So this part is fixed. Okay, plus maximum discharge time. Okay, maximum discharge time. So charging time is what? 2 to the power n Tc plus what is maximum discharge time? So in a 4-bit, it can discharge from 15 to 0. So in total, it will be what? 2 to the power n minus 1 Tc, or this is equal to 2n plus 1 minus 1 Tc. So this is what? This is your maximum conversion time of what? This is the maximum conversion time of your dual slope type ADC. Okay, dual slope type ADC. Now I will make one table for you. So type of ADC along with its conversion time. Okay, along with its conversion time. So first is what? Flash type ADC. So flash type ADC is the fastest, its conversion time is Tc. Next we have successive approximation type. In successive approximation type, we have seen one is your counter type, another is program type. So in counter type, what is your conversion time? It is 2 to the power n minus 1 Tc. And for your program type, it is your NTC. Okay, NTC, where n is the number of bits. And for dual slope, it is 2 to the power n plus 1 minus 1 Tc. So this dual slope is the slowest ADC, but it is also the most reliable ADC. Okay, most reliable ADC. So remember this, these points are asked in your GATE exam. Okay, GATE exam, it is asked what is the most slowest and what is your means least reliable. So all those things are asked over here. Okay, so if time is not the constraint, then we always use dual slope ADC. So with this, we finish our DAC and ADC chapter that is useful in your GATE exam for EC electrical IN. So in the next session, we are going to solve questions. Okay, so see you in the next session. Thank you.